Okay, let's look at the basic demographic parameters and their formal definition. First, instantaneous mortality rate is the foundation. We use as notation mu of x. Mu is the Greek version of the letter m, and x is the age. Is the probability of an x years old individual to die between age x and x plus dx. Then we have survivorship function, which is a function of age. We indicate with p of x is the probability of an individual at birth, that is at age x equals 0, to survive at least until age x. What is the relationship between the mortality rate and the survivorship? Well, let's look at that. We start by computing p of x plus dx, that is the probability that individual at birth to survive at least at age x plus dx. Okay, so we can indicate this with the axis of time. This is birth, this is the first age interval x, and this is the x small age interval. So we got p of x plus dx. Okay, so this can be computed as the product of two factors: the probability of surviving until age x and times the probability of not dying in the little interval, the x. This probability is equal to 1 minus mu x in dx, definition. So we can now compute p of x plus dx as the product of p dx, probability of surviving from birth to age x, times the probability of not dying in the little interval dx, which is 1 minus mu x in dx. Then we can multiply p of x times the terms that are in the curly brackets. We subtract p of x from each member, then divided by dx each member, and we basically derive the p of x plus dx minus p of x divided by dx, which is equal to minus mu of x in times px. And we know that when dx becomes really, really small, the incremental ratio that we have indicated in this way here can be represented as the derivative of p with respect to hx. So dp over dx is equal to minus mu x in px. We can now integrate this function by separation of variables, and so we can basically divide each member by px, so we get dp over p is equal to minus mu x in dx, and then we can integrate from p of x times 0 to p of small x to capital X of dp in dp equal the integral from x equal to 0 to small x equal to capital X, the interval of minus mu x in dx. And we know that the terms here, the primitive is the logarithm of p dx and is integrated through the integration interval, and this is just the integral between 0 and capital X of mu of x in dx. And so we can basically compute this as the logarithm of p of x, which is equal to the integral of between 0 and x of minus mu x in dx. And when we integrate, we basically derive that mu of x is equal to the exponent of the exponential of minus the integral of theta between 0 and x of mu dx in dx. And so these are the two terms that are relevant, and here this is the relationship between p of x and mu of x. Let's look now at the age distribution of death, which is referred to as the Greek letter gamma of x. And gamma of x times the x is the probability of an individual at birth, that is at age x equal to 0, to die between age x and x plus dx. So the relationship between the survivorship functions, mu of x, instantaneous mortality rate, and gamma x, the age distribution of death, is that gamma x is equal to the probability of surviving from birth to age x and the probability of dying in the small interval, the x. We can then divide it, both member, the left-hand side and right-hand side, by the x, and we derive exactly this function. Gamma of x is equal to p of x times u of x. Note that as the p over the x is equal to minus mu x times p of x, it follows that gamma of x is equal to minus dp over the x. And therefore, gamma of x is the probability density function corresponding to the probability distribution function 1 minus px, that is the probability to die before age x. So all these concepts are quite dense. So let's look also at a graphical representation on how, for instance, the instantaneous mortality rate can change with respect to age. And in ecology, we refer quite systematically to some typical mortality function. So the mortality function of type 1, it's a mortality that at the really small age starts from 0, so it's basically almost no mortality, and then increase more than linearly, possibly with age. And then there is a type 1b of mortality function that at age equal to 0 start with the value that is larger than 0 and then increase potentially more than linearly. The type 2 mortality function is just a flat horizontal line, so it's a constant mortality. There is no difference with age. And then we have, yes. The third type of mortality functions, type 3, is a mortality that decreases with age. I would say that is nature in a lot of cases. There are other mortality functions that apply. In a lot of cases, they might be what I refer to informally as a sort of a bathtub type of mortality function that is high in the early stages and drop down with age, and eventually might drop out and increase again with senescence of individuals. Given the type of instantaneous mortality rate function, let's have a look how survivorship P of X looks like. So if in the case of 1A type of instantaneous mortality rate, the survivorship function, which is the integral between 0 and x of the instantaneous mortality rate, is almost flat at the beginning, because mortality rate is basically equal to 0, and then eventually drop down. With the type 1b of mortality function, of course, we always start from 1, but the derivative there is negative, and it dropped down faster than in the case 1a. In the case of a flat mortality rate, a constant mortality rate with age, we just have an exponentially decaying survivorship function, which is equal to e to the power of minus mu x. And in the case of type 3 mortality function, we have a survivorship that drops even faster. And it's all, I think, makes sense intuitively, because if the mortality rate is really high and drop down fast at the beginning, the probability of surviving is actually really low. And then, it just continues to drop down. Please note that the survivorship function, in the way it's defined, it's a monotonic decreasing function of age. So it can be at most flat, but otherwise the derivative, the first derivative, is always negative. If we look, in fact, that in semi-log scale where we report here survivorship in a logarithmic scale, this is a decimal logarithmic scale, well, the exponential function, when the mortality rate is constant, it becomes, as we know, a straight line. And these represent very clearly the difference between the type 1 and type 3 mortality function. In the case of type 1 mortality functions, we can see lots of individuals have a high probability of surviving to old ages. In the case of type 3, there is a high death rate in the early ages, and so the probability dropped down very quickly, and only few individuals might survive to really old age. And type 2, of course, is intermediate function. Let's have a look at the age distribution of death. And in the case of 1A mortality rate, so we do have mortality rate here. Let's look at the probability of surviving until age X, and then the age distribution of death. So in this case, we have seen that the mortality rate at the beginning is very low. So we actually expect that very few individuals I've known will die at the early ages, and then will increase and be maximum here. And in fact, if in the case 1A, the mortality, the age distribution of this might be represented like sort of this bell-shaped function there. In the case 1B, we'll start to lose individual even in the early stages, and so there's going to be few individuals who have some probability of dying at the early stages. And in the case it's flat, we are going to have also an exponentially decreasing probability of survival until age X, and also age distribution of death is going to be characterized by an exponentially decreasing function. And this is the case of a type 3 mortality rate, in which the age distribution of death is largely biased in the early in the early years of life. Let's move forward and use this information to derive other important parameters. For instance, life expectancy at birth, which is usually indicated as E0 here, is the mean number of years an individual at birth is expected to live. It can be computed as the mean of the age distribution of death. So E0 is computed as the integral between 0 and infinity, the maximum age of the mean of gamma of x in dx, because we know that gamma is a density probability distribution, and so this is the way we compute the mean. And we can use the information that we have, because gamma of x is equal to minus dp over dx, we can substitute this into this function here. And what we derive is that E0 is minus x in dp. And after a little bit of algebra here, we derive that E0 is equal to the integral between 0 and infinity of p of x in dx. So it's the area that underlying the survivalship function. Now, another important parameter is the life expectancy, not at birth, but at age X, which is here indicated as f of x. This is the average number of years that an individual at age X still expected to live. So it's an individual that has lived until age X, and and we wonder how long, on average, is still expected to live. This can be computed as the integral between 0 and infinity of gamma of x plus tau times tau in d tau divided by the probability of surviving, so conditioned to the probability of surviving until age x. And even in this case, by using the property that gamma of x is equal to minus dp over dx, we derive this function here. So it's basically the area under the survivalship function starting from age x to infinite divided by to the maximum age divided by the value of the survivalship function at age x. So the probability of survival from age 0 until age x. There's an interesting property here, because in the case the mortality rate is actually constant, we can show that E equals 0, which is this integral between 0 and infinity of p dx and dx, and so because p dx is equal to E minus mu x, well, if we do all the integral, we derive that this is equal to 1 over mu, which is actually very useful, because in a lot of cases for some species, we have some ideas of the lifespan on average and the mean life expectancy, and we can use it to derive a ballpark of the mortality rate. But another interesting aspect here is that when mu is equal constant, the life expectancy at age x that is computed in this way is again equal to 1 over mu. So regardless how long an individual is asleep, because the mortality rate is constant, its life expectancy from that age forward still remain the same 1 over mu on average. Another important function is the net maternity function, or reproductive value, that is indicated here with the Greek letter phi of x, is the mean number of female offspring that a female at birth is expected to produce at age x. So for continuous time models, is derived as the probability that an individual, a female, has to survive from age 0 to age x, or P of x, times the fecundity rate at that age. In the case of discrete time reproduction, where there is a seasonal reproduction, very concentrated, rather than indicated with phi of x as a function, we just use the suffix x, so phi of x is equal to the sum over all the reproductive ages on the fecundity rate divided by the sex ratio. Here we assume that mu of x already accounted for sex ratio. Here we explicitly mention or refer to the sex ratio. So is the fecundity at that age times the probability of surviving from birth to age x. The net maternity function is really important because it's the foundation that is used to compute a really important parameter, the reproductive number R naught. That has been defined in demography, and we heard a lot about that, talking about epidemics of COVID-19, the reproductive number. And in this case, in ecology, reproductive number is the mean number of female offspring produced per female over her lifetime. For continuous reproduction is computed as the integral of phi of x in dx, the integral of the net maternity function, which is this one. For discrete time reproduction, the synchronized birth, the seasonal reproduction, this is computed as the sum over basically all the reproductive ages of 1/2 x, so the fecundity divided by the sex ratio times the probability of surviving until age x. Now, R naught equal to 1, let me take a little break here. Sorry for the small interruption. So, R naught larger than 1 means that a female is able to more than replace herself along her entire reproductive life. So R naught is really important. Basically, R naught larger than 1 means that population has this potential of growing in time. As a consequence, if R naught is larger than 1, then the finite growth rate lambda is larger than 1. And we also know that means the instantaneous per capita growth rate, small r, is larger than 0. So it's a growing population. And one important aspect here is that although lambda is generally considered equal to e to the power of r, in general, R naught is different from lambda. Okay, so R naught both is in a stable population, lambda is equal to 1 and R naught is equal to 1 because over the entire reproductive lifespan, a female is able to replace herself, and so the population is constant. But otherwise, R naught and lambda are different. Of course, if lambda is larger than 1, then we expect R naught to be larger than 1, and vice versa. If R naught is smaller than 1, then we expect lambda to be smaller than 1 and the population to decrease. The reason why they're different is that R naught is in fact measures over the entire reproductive lifespan of the population, while lambda is the finite growth rate of increase over a specific amount of time. For most of the population that have a really reproduction is from 1 year to the next year, for instance, this or the time interval between 2 reproductive season or event. And only in the case of the annual semi-annual population, we got that R naught is equal to lambda. R naught scales with the generation length TC, and therefore depending upon how long is the generation, if we say that the number of individuals are after TC time or years is equal to lambda to the power of TC times N0, which R naught that is equal to NTC divided by N0, roughly being equal to lambda to the power of T. Okay, so over a time interval that is similar to the length of a generation, in that case, R naught is equal to lambda to the power of T. And that means that lambda is approximately equal to R naught to the power of 1 over Tc. We just use the term generation length, but we haven't really defined that formally. And there is a way, there are several ways of doing that, but one way of doing that is to compute the mean age at which females reproduce their offspring. So it can be computed starting from the maternity function, f of x equal to p of x times nu of x, and Tc is equal to the mean age at which females produce their offspring. F of x, as we computed before, is not a density, a probability density, and so in order for that to be, we need to be sure to integrate between 0 and infinity phi of x in dx, and to divide phi of x times this number here, so that the integral between 0 and infinity of phi of x divided by this denominator is equal to 1. And when we look at this denominator here, we know that the integral between 0 and infinity of phi of x and dx is equal to R naught. And so the length of the generation can be computed as the integral of x and phi of x divided by R naught. Now, let's go to the last part of the presentation here. That's the definition of life tables. The life tables follow the fate of a group of individuals that are all born in a specific time, for instance, in a specific year. And we refer to that as a cohort of individuals. And we follow these individuals until they die. It's really great when it's possible to derive a life table, because we can basically derive a lot of information about the basic demographic rate as a function of age, even when the population is not stable over time. Although I also have to mention that its life tables can be found, for instance, for marine mammals, and in some specific cases of species that have a fairly short lifespan. Otherwise, it might be difficult to follow a cohort of individuals for several years and potential for decades. Another classical element is what you can get from a census, sort of a snapshot of the current age structure that is might be derived, for instance, assuming age distribution. And it can be used to derive demographic parameter so long the population growth rate is known. A very specific type of snapshot of a static life table is when we can, for instance, derive the age of the death observed. So basically the distribution of age in the individual that died by, for instance, looking at the otolith in fishes or teeth in marine mammals. And so if we can do that, we can use this information to derive also the basic demographic parameter. And in a lot of cases, we use all the information that is available, and we cross the information to get the best estimation of the demographic parameter. We mentioned before the dynamic life table and the static life table. So the snapshot, the cross-sectional static life table is when you go in a certain year and we take a snapshot and we do an estimation of the age of the individuals. And so that would basically be a static life table. And dynamic life table, when we look at the cohort individuals, for instance, all the individuals that were born in 1968, and then we follow this individual year after year, and we see, of course, their number decreasing in time. And so this is called a dynamic life table. And every year that goes by, those individuals will, if they survive, of course, they will be 1 year older. There is an interesting aspect is that, for instance, if the population is not stable, but is growing, like in this hypothetical example, when we look at the number of individuals out of the census, and then, for instance, at age 9, 48, and then we follow the cohort of the individual, well, we expect that number to increase because the population is increasing in time. And so we can see in this life table, assuming, for instance, a 4.6 rate of growth per year in this hypothetical case. Now, let's have a look again to sort of a hypothetical case, which is being inspired by the demographic parameter life table presented by Sterling and Borrow in a paper published in 2003 on marine mammal science. And it's demographic information relative to the life table of bottlenose dolphin, Tursiops truncatus, in the Indian River lagoons in Florida. Here we assume the sex ratio is 1:1, and we also assume here that the fecundity, as represented here in this column, is the mean expected fecundity that already account for the fraction of females that are actually reproducing, that are not all of them, and those that are able basically to generate offspring. So it accounts for reproductive success. So let's see how it works, and let me take again a little break here to so let's take our life table here. So we have X, the number of individuals of age 0, 1, 2, 3. So we follow this cohort. The root of this cohort is equal to 135 individuals that were tracked year after year up to their maximum lifespan of about 34 years. We also had information of the fecundity that was already accounting for the probability of reproducing and reproducing success. So as you hear, I have derived a number of other parameters, so let's look at them one at a time. Okay, so we have here, I would say, X and N of X. Well, we can derive here on the third column, P of X, that's the fraction of individuals in the cohort surviving to age X, which is equal simply to NX divided by the root of our cohort, N0. And so we have derived here these survival rate functions for each observation that we have. We can compute dx, which is individuals that die between age X and age X plus 1. And so we got 8 individuals that are dying in this cohort from age 0 to age 1. So we report here the difference of 135 minus 117, which is equal to 18. And then 117 minus 109, which is equal to 8, and so on and so forth. And then we can compute Q of X here, which is the fraction of individuals to die between age X and age X plus 1, which is equal to dx over nx. So we have 18 individuals stayed between age 0 and 1 over 135. So 18 divided by 135 is equal to 0.133. We can see, we'll see that in the lab that this fraction of individuals that died reflect how many individuals they might happen to die year after year. Like, for instance, here for a few years, no individual died, and so the Q0, the Q of X is equal to 0 to reflect the fact that the number of individuals remain constant. So that does not really mean that the mortality rate is equal to 0, but simply that no individual died during that time interval. So we can use, in this case, I've used a quadratic function to smooth down the fraction of individuals dying between age X or X plus 1. And then I use this information to recompute P of X on the basis of the interpolating value, okay, and which is reported here as because P of X plus 1 is equal to P of X times sigma X, and sigma X, which is the fraction of individuals surviving from age X to age X plus 1, is nothing else than 1 minus QX smooth, so the fraction of individuals that are not dying during the time interval. So I can compute this one. And we have seen, this is what we had already, was given by the authors of the paper. So we can then compute for each age class 1/2 times fx, which is the net fecundity, so number of female offspring generated by a female at age X, multiplied by the probability of surviving until age X. Of course, these values are equal to 0 until age 8, that is the age at forced reproduction. So we can use this information now to basically so we can finally compute some information about this population, the life expectancy at birth, which is equal to the integral between 0 and the maximum age of the probability of surviving until age X in the X. And we can approximate this by using the trapezoid methods. I'll show you in the lab. And they would be equal to simply 1/2 plus the sums of the probability of surviving exactly at age 1, 2, 3, 4, etc., etc. And we'll see that this is equal to 11.7 years. Then we can also use the information on the net maternity function of the reproductive value that we computed before. And by summing this up, all the reproductive age, we found that this is equal to 1.96, and years is wrong, it's just 1.96, sorry about that. We can use also this information with the Euler-Lotka equation in this model to compute the only unknown parameters that we still have, the lambda, and we use this as the Euler-Lotka equation, and by solving this equation numerically, we found that lambda is equal to 1.04467, so about 4.6% of growth every year. And we can also see clearly how R0 and lambda are different here. So with this, we end up this part of the class. We discussed the importance of age and of size for mortality and fecundity. We derive age structure demographic models. We did it for the Bay anchovy, for the killer wave. We derive all the basic properties of these models. So these are matrix models with constant coefficient, and we've seen that if this case, if there are no density dependency, the overall population growth in Malthusian way, the population in each age or size or stage classes also increases in an exponential way. In the long run, the proportion of individual in each age or stage or size classes become constant in time. We also saw that the initial growth is strongly dependent upon the initial population structure. We presented other property of the age, stage, size structure models. We derived the Euler-Lotka equation for the Leslie model, and we also saw how we can use the properties of the transition matrix to compute, for instance, the finite growth rate of the population or the long-term stable age or size distributions. And last but not least, we can use this information also to derive elasticity and to understand how the finite growth rate is affected by relative changes in the different model parameters that contribute to the definition of the transition matrix. And last but not least, we have derived a formal definition of the most important demographic parameters, and so how we can use, for instance, information like tables or census to basically estimate these demographic parameters. Thank you very much for your attention. My apologies that this video recording has been interrupted by a number of times. Thank you for your patience.